Imagine a future where scientific breakthroughs aren't just made with AI's help, but maybe, just maybe, they're actually led by intelligent machines. Is that really possible?
That's definitely the provocative question we're digging into today. We're looking at something new from Google DeepMind.
Right, this thing called AlphaEvolve, a coding agent, they call it. And its job is basically finding new science, creating better algorithms.
Yeah, essentially it takes these powerful large language models, the AI trained on tons of text and code, and puts them into an evolutionary process.
Evolutionary, how does that work with code?
It iteratively refines algorithms.
Hmm.
It actually changes the code directly line by line sometimes,
Okay.
and it uses feedback, like scrolls from evaluations, to figure out which changes are actually improvements.
So AI is moving beyond just assisting us. It's tackling these really hard, open problems, even optimizing like the core infrastructure of computing. Feels like we're getting a glimpse into the future of R&D here.
I think so. And for this deep dive, our source is a pretty detailed white paper that lays out how AlphaEvolve was built and what it's been used for.
Great. So, our mission today, unpack what AlphaEvolve can do, what it's already achieved, and importantly, get a feel for how it actually works underneath.
Sounds good.
Okay, let's start there. This idea of an evolutionary coding agent. What does that mean in like practical terms?
It's basically an automated system. Think of it orchestrating these large language models, LLMs, to improve algorithms over time.
So it's a loop. Generate, test, learn.
Pretty much. The LLMs suggest code modifications, those get tested automatically, and the feedback tells the system whether it's moving in the right direction.
So it's not just random changes, there's some intelligence guiding it.
Right. That feedback loop is crucial. It steers the evolution towards better solutions. And the hope is, finding genuinely new things, scientifically or practically useful things.
That sounds powerful. The paper mentions it's been applied to a really diverse set of problems. Where has it made a difference so far?
It's shown some real versatility. Uh, for instance, they used it to optimize scheduling algorithms in Google's data centers.
Okay, real world impact there.
Definitely. Also, simplifying hardware accelerator
Mm.
design the chips that power AI, and even speeding up the training of LLMs themselves, including, interestingly, the models that AlphaEvolve relies on.
Whoa, it's optimizing its own foundations. But the paper also talks about finding completely new algorithms in math and computer science. That sounds huge.
It is, and we're not just talking small improvements. These are, in some cases, provably correct algorithms that are better than the best we've had before. The matrix multiplication result is probably the standout example.
Ah, yes, the 4 by 4 complex matrix thing. I saw that. Why is that particular result such a big deal?
Well, for 56 years, the record for the number of multiplications needed for that specific task was 49, based on Strassen's algorithm. AlphaEvolve found a way to do it in 48.
Just one less multiplication.
It sounds small, but matrix multiplication is absolutely fundamental. It happens billions, trillions of times in scientific computing, AI, graphics, everywhere. Shaving off even one operation in the core algorithm can have massive ripple effects. And nobody had improved on that specific number for over half a century.
Okay, that puts it in perspective. So what's the process? How does AlphaEvolve actually do this? What's going on under the hood?
Well, first, it needs problems where you can automatically evaluate a potential solution. You need a way to score how good an attempt is.
Right, needs a target.
Exactly. The candidates, whether they're mathematical objects or maybe practical heuristics, are represented as algorithms, as code.
Okay.
Then the LLMs come in. They generate new code, they critique existing code, they basically evolve these algorithms.
But how does it avoid just suggesting nonsense code?
That's where the execution and evaluation come in. By actually running the generated code and scoring its output automatically, the whole process stays grounded in reality. It filters out incorrect or useless suggestions.
So try, test, learn, repeat.
That's the evolutionary cycle. And over many cycles, you can arrive at solutions that look very different from where it started, both in the code itself and in how the algorithm actually solves the problem. Sometimes the algorithm is the goal, sometimes it's a tool to find something else.
The paper compares it to an earlier system, FunSearch. What are the main upgrades that AlphaEvolve brings?
Oh, there are several key differences. AlphaEvolve works on whole code files, not just one function. And it can handle hundreds of lines of code, way more than the 10 or 20 lines FunSearch could manage.
Gives it much more room to maneuver, creatively speaking. What else?
It's language agnostic now, not just Python. The evaluation can run for hours, even days, in parallel on accelerators, whereas FunSearch was limited to maybe 20 minutes on a single CPU.
Big difference in search power.
Huge. Yeah. And interestingly, it needs fewer LLM samples, thousands instead of millions, It seems to get more out of the modern, more powerful LLMs. It also uses much richer prompts with lots of context and feedback compared to FunSearch's minimal approach. Plus, it can optimize for multiple goals at once, not just a single score.
Sounds like a major step up across the board. The paper has a diagram, figure 2, showing the workflow. Can you walk us through that loop quickly?
Sure. It starts with the user providing some initial code, the evaluation logic, and maybe some configuration. Then it enters the evolutionary loop.
Okay.
A prompt sampler picks good programs from a database of past attempts. It uses these to create detailed prompts for the LLMs.
Prompts are like instructions for the AI.
Kind of, yeah. Instructions plus context. The LLMs then generate changes, these diffs. The diffs get applied to create new programs. These new programs are evaluated and scored.
And the good ones.
The promising ones go back into the database, influencing the next round of prompts and generations. So it keeps building on success.
That makes sense. How much control does the user have over those prompts, the instructions for the AI?
Quite a bit, actually. You can give it explicit context, problem descriptions, equations, code examples, even pointers to research papers. There's something called stochastic formatting, which varies the prompt structure a bit to get more diverse outputs. The prompts also include results from past evaluations, what was tried, what happened, what the scores were, and there's even meta-prompt evolution, where the LLM itself suggests ways to improve the prompts being used.
Whoa, the AI helps improve its own instructions. The paper really stresses how important the quality of the LLM is for this creative part.
Absolutely. You need these state-of-the-art models, like the Gemini series mentioned, to properly digest all that context and make genuinely insightful suggestions for improvement. They use an ensemble, a mix of models, to get both speed and quality, and the way it suggests changes uses a specific format, search and replace blocks, to be very precise about modifying the code.
Okay, so the LLM proposes a change. How is that change actually judged, the evaluation part?
It's automated using code the user provides. That keeps it objective. There are also optional, more advanced mechanisms.
I like what?
There's an evaluation cascade. Think of it like a series of tests getting progressively harder. It quickly weeds out bad ideas. You can also use LLM-generated feedback for things that are hard to score numerically, like code simplicity.
Ah, okay.
And of course, evaluation can run in parallel across many machines to speed things up. Plus, as we said, it can track and optimize several different scores simultaneously, even if one is the main target.
Balancing different objectives. Makes sense for complex problems. What about this evolutionary database and the distributed pipeline? Quick rolls.
The database just stores everything: programs, scores, history. It uses strategies inspired by things like MAP elites and island models to manage this population effectively, balancing exploring new avenues with exploiting known good ones. The pipeline is the infrastructure controller, samplers, evaluators, all working together asynchronously to process as many candidates as possible.
Got it. Let's circle back to that matrix multiplication result. Why is beating that 56-year-old record so fundamental?
Because matrix multiplication is just everywhere in computing. It's a basic building block. Making it faster, even slightly, makes tons of other things faster. AI training, simulations, graphics.
And AlphaEvolve didn't just tweak the old method, it found a fundamentally different approach.
Yes. It developed new mathematical ways to decompose the problem, represented as tensors, which led to fewer multiplications. The evaluation was rigorous, multiple checks, ensuring the result was mathematically exact. And it wasn't just the 4x4 complex case, it improved the state of the art for 14 different matrix multiplication variants overall.
Wow.
Yeah, the paper shows examples where the final algorithm looks very different from the starting point, showing real innovation. They also mentioned that giving it some human ideas initially could potentially boost it even further, hinting at human-AI collaboration.
Fascinating. Beyond that, you mentioned it tackled open problems in pure mathematics, over 50 of them.
That's right. Across different fields, trying to find mathematical structures or objects with optimal properties, it managed to rediscover the best-known solutions in about 3/4 of the cases it tried.
Which suggests those known solutions might already be optimal.
Potentially. But what's really exciting is that in roughly 20% of the problems, it actually surpassed the state-of-the-art, found better solutions than humans had previously discovered.
Can you give a couple of examples? What kind of problems are we talking about?
Sure. In analysis, it found tighter bounds for certain inequalities, things related to signal processing and uncertainty principles. In combinatorics, it improved the bound for a classic problem called Erdős' minimum overlap problem.
Okay.
And in geometry, probably the most intuitive one, it improved the lower bound for the kissing number in 11 dimensions. That's the maximum number of identical spheres that can touch a central sphere without overlapping. The record was 592. AlphaEvolve found a configuration for 593.
Just one more sphere, but in 11 dimensions, finding that arrangement is incredibly hard.
Extremely hard. And it also found new results for other packing problems. Many of these were problems suggested by mathematicians, highlighting that potential partnership again.
It's incredible stuff, but it's not purely theoretical, right? The paper details how it's optimizing Google's own infrastructure. Let's get into those practical wins.
Absolutely. This is where you see the immediate large-scale impact.
First up, data center scheduling. That sounds like a nightmare problem.
It's hugely complex. Assigning all the computing jobs efficiently across thousands, millions of machines in Google's Borg system. Wasted resources add up fast. AlphaEvolve was used to evolve the heuristic, the sort of rule of thumb, used for assigning jobs based on CPU and memory needs.
Yeah.
It found a surprisingly simple modification to the existing heuristic that turned out to be very effective. They tested it in simulation, then rolled it out across the whole fleet. The result was recovering, on average, 0.7% of Google's fleet-wide compute capacity.
0.7% doesn't sound like much, but at Google's scale.
It's enormous. And they chose AlphaEvolve partly because the resulting heuristic was understandable and easier to trust and debug in such a critical system compared to maybe a black box deep learning approach.
Interpretability matters. Okay, what about improving the Gemini models themselves?
Training models like Gemini involves massive computations, especially matrix multiplications run on specialized hardware like TPUs. How you break down these big calculations into smaller chunks, the tiling strategy, really impacts speed. It's usually hand-tuned by experts.
A difficult job, I imagine.
Very. AlphaEvolve was set up to automatically optimize the tiling heuristics for a key calculation kernel used in Gemini training, aiming to minimize the actual runtime on TPUs.
And did it work?
Yeah, it achieved an average 23% speed up for that specific kernel, which translated to about a 1% reduction in the overall training time for Gemini. Plus, it cut the optimization time from months of human effort down to just days. That improved heuristic is now running in production.
Months to days, plus a speed up. Impressive. And it even helped design the hardware, the TPUs.
Right. Chip design is another super complex, long process. They challenged AlphaEvolve to optimize a small but critical arithmetic circuit in a TPU, described in the hardware language Verilog. The goal was to reduce its area and power use without changing its function.
Yeah.
It found a simple code change, removing some unnecessary bits, which hardware designers confirmed was valid and useful. That improvement is actually being integrated into an upcoming TPU generation. It's Gemini, via AlphaEvolve, directly contributing to hardware design. And the fact it works directly with Verilog is a big plus for the engineers.
AI designing its own future home, in a way. Amazing. Lastly, optimizing compiler output.
Yes, this was about taking the low-level code generated by the XLA compiler for a key AI component, flash attention, and optimizing it even further.
Wow.
This compiler code is already highly optimized, so it's a tough target.
Squeezing out more performance.
Exactly. Every change was checked to ensure it didn't introduce numerical errors. It managed significant speedups, 32% for the main flash attention kernel and 15% for some surrounding code. This suggests these kinds of AI-discovered optimizations could potentially be built into future compilers.
Wow. Okay. The paper wraps up with some ablation studies. What did those tell us?
Basically, they switched off different parts of AlphaEvolve one by one: the evolutionary aspect, the rich context and prompts, the meta prompts, evolving whole files using powerful LLMs, and tested the impact on performance for problems like matrix multiplication and sphere packing.
And the conclusion?
The main finding was that pretty much every component contributes meaningfully. It's the combination of all these elements that makes AlphaEvolve so effective. Each piece plays an important role.
Okay, so bringing this deep dive to a close, what are the main takeaways here about AlphaEvolve?
I think the core message is that this combination state-of-the-art LLMs, automated evaluation, and this evolutionary framework, it's proving to be a really powerful engine for discovery. We're seeing breakthroughs in fundamental math, computer science, and also in optimizing really critical real-world systems.
That 4x4 matrix result and the wins on those open math problems really stand out as milestones.
Definitely. But the practical impact is just as important: optimizing Google's data centers, making Gemini training faster, improving TPU designs, speeding up compiler code. It shows the breadth of its applicability.
And it seems quite flexible in how it tackles problems, sometimes searching directly, sometimes evolving ways to build solutions, sometimes evolving search strategies themselves.
Exactly. And looking ahead, there's potential to distill what AlphaEvolve learns, back into future-based LLMs, making them inherently better problem solvers.
The need for those automated evaluators is maybe the main limitation right now, but they hint at maybe using LLMs for feedback in the future too, which could open up even more areas.
It definitely points towards a future where these tools are much more integrated into the scientific and engineering process. Which leaves us with a final thought for you, the listener. How do you see tools like AlphaEvolve changing science and tech in the coming years? And what does the partnership between human experts and these AI discovery engines look like?